Good evening and welcome to tonight's webinar, Help My Students Want to Know About Nanoscale Science and Engineering. I'm Quinn Spadola. I'm a contract staff at the National Nanotechnology Coordination Office, and I manage our education outreach efforts. One such effort is the Teaching Nano and Emerging Technologies Network. And if you're interested in learning more, you can go to that webpage. The address is right there up on the screen. And I also want to point out the Nano Education resource portal. And many of the resources that Nancy will be discussing this evening are on that searchable database, so you should definitely check that out. And lastly, this webinar will be archived on NanoTube, the National Nanotechnology Initiative's YouTube channel. And you'll also be able to find a link on www.nano.gov/public-webinars. And you'll be able to find our two previous webinars as well. One was an overview of a year-long high school nanoscience class, and the other explains remotely accessible instruments for nanotechnology. So now on to tonight's webinar, and we will be hearing from the wonderful Dr. Nancy Healy. She is the Associate Director for Education and Outreach for the National Nanotechnology Coordinated Infrastructure, a National Science Foundation funded network of user facilities. And she oversees the NNCI's education and outreach programs and did the same for the NNCI's predecessor, the National Nanotechnology Infrastructure Network, the NNIN, from 2004 to 2015. And she will be taking questions at the end. So please just type those into the question pod as you have them. And with that, I'm very much looking forward to hearing about the NNCI's K-12 efforts. So I'll turn it over to Nancy.
Okay, so welcome everyone. As I am located at Georgia Institute of Technology and the Institute for Electronics and Nanotechnology. So, okay, my first question is, how do I advance slides? Quinn?
Yes, it's the bottom, on the bottom and the left. You see the little arrows? The little arrows to the bottom, to the left of the slides.
Yes. Good. Okay, now we can move forward. So,
great.
So the NNCI is the National Nanotechnology Coordinated Infrastructure, which is funded by NSF and is part of NNI's mission to have resources and facilities. This is what we look like. We're 16 sites, 13 partners, and we are in 17 states. Our goals are to have an open access, state-of-the-art nanofabrication facilities. When we use these resources to support education and outreach, as well as social and ethical issues. We are the successor, as Quinn said, to the NNIN, which existed from 2003 to 2015. But these NSF-funded nano networks have a long history. It started at Cornell in 1987, then became the NNUN in 1993 with 5 institutions. Those 5 institutions were part of the 14 under NNIN. So the federal government has had a long time of supporting this and supporting nano education. So our education and outreach mission is focused on a skilled workforce and an informed public. We want to use our resources and materials to enhance nano knowledge in its real-world applications. And again, it's all because we think the U.S. economy needs to have a STEM literate and informed citizenry. So these are the programs that NNCI is actually involved in. At the top of here, you can see this is the groups that we are reaching. And these are the various programs that we have as part of the 16 sites. Not every site does every single one of these, but a majority will do certain ones, and in particular, a lot of K-12 outreach and our research experience for undergraduates is at 2/3 of the sites. So why nano education? Well, it's it's advancing very rapidly. We have more than 1,600 consumer products right now on the market that use nanotechnology, which is a 25% increase since 2010. So if we're going to have this rapidly advancing technology, we need a workforce, and we feel that K-20 education and outreach should be a major thrust of our universities and our federal labs, and hence that's the reason that we have this program. So why should you know something about this? So I'm using the Georgia data. These are the STEM report cards that come out from U.S. Innovation. And as you can see here, there's about a 9% increase needed for jobs between 2016 to 2025. And U.S. STEM jobs are supposed to grow by about 17% compared to 9.8% for non-STEM. And the NSF estimates that we need 2 million workers worldwide in this field, with about 1 million of those in the U.S. And Lux Research estimates that this is going to be about a 5% of our gross domestic product by 2020. So it's really a critical area for jobs. Then I went and looked at some of the other state STEM data to convince I'm probably speaking to the preaching to the choir here, but I went to all the rest of the NNCI sites, and as you can see, most of them average about 10% increase in job needs. And the last one that I want to show to say why we need to do this, we are seeing an increase in STEM interest, so obviously we're doing a good job. We're seeing an increase, but as you can see, the male to female, we're not doing such a good job on females. But American Indians, Asians, African Americans, Hispanics, and white all show a strong interest in STEM. But research has shown that females and minorities respond to science and engineering fields that are seen as helping. And that is where nanotechnology comes in, because we can show students real-world applications and how they can help consumers. Also, the salary earnings are really good. Typically, the average salary at this low end is for those that get associate degrees and work as technicians in lab, and then I would say this is probably faculty. And the final push of why we need to do this, this is just a really great example of all the areas that nanotechnology is reaching. It's in just about every sector in every part of our lives, so we need to know about it. So everything always begins, what is nanoscale science? And it's the understanding and control of matter at the dimensions between 1 and 100 nanometers. And at that area, unique phenomena occur which enable novel applications and novel products. So as I stress, I just had a group of kids in yesterday, and I stressed to them unique properties. That's one of the key things about nanotechnology. And the other thing is it's interdisciplinary. It's where science and engineering interconnect. So at the nanoscale, we have these unique properties. Essentially, at the nanoscale, things behave under atomic and molecular rules. So we look at the gecko's foot. The gecko's foot, no one could quite figure out why it was such a great animal that could walk up the walls and across the ceilings, and it came down to that it had hundreds of thousands of these little tiny hairs that ended in these nice little cubic pads, and these setae allow it, using van der Waals forces, to attach to the walls and disattach to the walls. And at the nanoscale, van der Waals is a very strong force, but in our world it's a very weak force. So nano is not new. Here's the gold we all know, but gold at the nanoscale, these are different gold nanoparticles are different colors. And medieval glassmakers did not know they were doing nanotechnology, but as they ground down silver and gold and put these salts into their glass making, they got these beautiful colors. And then all the way back to 400 AD, the Lycurgus cup, developed by the Romans, has nanoparticles in it, and depending on whether you look at it from the front or the back, the way the light is coming through, it appears red or green. They don't know how they did it, but they did it. So how do we make things? As I said, we are a facilities network, and in our labs we do things either through top-down fabrication, essentially start with a large piece of material and we etch it down typically with chemicals. And then we have bottom-up nanofabrication, which is where we take the individual atoms, create molecules, and build nanostructures. So those are the two ways we make things in our clean rooms. So how does it connect to STEM? As I said, it's interdisciplinary, and a lot of the lessons that we do connect to math, science, technology, and engineering. So why should your students know something about? What should your students know? And we have done essentially a lot of professional development and a lot of camps with students, and we have used the big ideas in nanoscale science and engineering as the foundation for our work. I think it's just a great resource for being able to look at nanoscale properties and how they relate to the curriculum. So these are the big ideas that came out of the book, and if you look at these, they're very much what is typically taught in the science classroom: structure of masses, matter, forces and interactions, size and scale, quantum effects, science and technology. So let's look at a big idea. This is just an example. The big idea will always have a definition of what the big idea is, and then the associated learning goals. So for this one, size and scale, which is very important in nanotechnology, factors relating to size and geometry help describe matter and predict its behavior. And then you can look at these learning goals to help guide the curriculum. So the advantages of using the big ideas is that they provide the core concepts to develop understanding of nanoscale science and engineering, and we found it was a way to make correct connections in the curriculum, help with understanding content knowledge, and it allowed us to take the nanoscale concepts and merge it into the curriculum. One of the things that we have been adamant about is that nanotechnology is not something to be added on, that it should just be included in your teaching. So teach a lesson, but give it a little bit of a nano twist, and kids will learn something about nanotechnology while still learning their content. One of the things that we've stressed when we do teacher workshops is the interdisciplinary nature of nanoscale science and engineering, and we want to help teachers and students to make the connections between nano and the current curriculum that is being taught. Also, we always want to stress that there are career opportunities. So we have a lot of experience in doing teacher workshops. We have reached at least one, but typically many more, of teachers in 46 of the 50 states plus Puerto Rico, and we reached at least, there's a typo, one teacher, but typically many more, in 100 of Georgia's 159 counties. So now we're moving on to NNCI, and hopefully we'll have great success there too. So where do we begin? Well, we're an odd group. We felt that we needed to talk to teachers. We wanted to ask them what were their needs. And so way back in 2005, 2006, we started going to the NSTA. And as I tell everybody, we were the loneliest booth at the NSTA because people walked by and just looked at us like, what is nanotechnology? But we dragged people in, and we did some focus group meetings to find out what was needed. And we learned that people have very little knowledge about nanotechnology. We found out where their source of information was, and that was news media and publications. But the thing we really wanted to know was what type of materials did a teacher need. At this time, the National Science Foundation was funding these big curriculum unit development projects so that they would create something that was 4 to 6 weeks, big, huge units. And we talked to teachers and they said, no, we need a short activity that's tied to a required concept. And then the next biggest one was a required concept, but it could evolve out to a 2 or 3 week unit. And what they wanted was online units and workshops, and so that's how we developed. We did these surveys through 2010, and the results varied very little. So that's how we decided we would do our teacher workshops based on what the needs were. The other project that we were involved in was called NanoTeach, which ran from 2008 to 2013, and it was a research project to determine what was the best way of getting teachers to learn about nano and how to incorporate it into their curriculum. And there were two groups. There was a self-paced teams and then a face-to-face professional development model. I'm sorry, I'm starting to lose my voice again. What we learned is that both methods assisted teachers in integrating these topics. Both groups, and this is very important, both groups reported high levels of student engagement and interest in learning science in nanoscale science and engineering. I will say that those teachers that were in the face-to-face had a much easier time of learning the concepts and learning how to enter it into their curriculum. I think there was some struggling with the group that was the self-paced. But all of the teachers that were in this project indicated that when you want to include nanoscale science and engineering in your classroom, you must begin with size and scale. So what is nano? It's an SI prefix. It means it's 1/1,000,000th of a nanometer. And where should we include it? Well, size and scale and SI measurements. And there are several of these type of size and scales that you can post in your classroom. We had teachers that developed in their bulletin boards the word macro, micro, and nano, so that when they were teaching their class a concept, they would say, where are we in this on the size and scale? And the students would be able to say, oh, today we're doing something in the macro world, or today we're doing something in the micro. And that tied that size and scale throughout the entire semester-long course. So one of the units that we like to use is NanoSense. This is one of those big, huge units that was created with NSF funding. So there's this one is size matters, and we like to use the one scale of objects. And it's a size sorting activity, and we have done this with thousands of students and teachers and even graduate students. And all it simply is they're given a set of about 20 cards with images on them, and they have to sort them. So they have the macro, micro, nano, and atomic world to look at, and they have to sort them. Another great way of doing size and scale is with interactives. There's some excellent interactives out there that students can then take their time to sort out where they are on the size and scale. And of course these will be posted on the website, but there's some really excellent ones, and they can reach all levels of students. So let's explore some ways of introducing nanoscale science while also addressing science standards. First, I want to talk about on the NNIN website, which is slowly going away and it will become the NNCI website. We have about 100 lessons on there. These lessons were developed by teachers, for teachers, and tested in the classroom. And I think that makes a huge difference if these have been developed by teachers because they're meeting the needs of their teaching. And all of them have the same format. So there's a purpose for the lesson, the time required, the level and subject area, the big idea that it's connected to, usually a very lengthy teacher background, so you're not going in cold on what the nano connection is. There's a material section, safety, advanced prep if that is needed. There's always a directions for the activity with the answers that is tied to the student guide that the students get. There's additional resources. We've tied them to the standards. Originally, they were the National Science Education Standards. We went back in once the NGSS came out, and we added that onto all of the lessons. And then some of them, because we changed our format a little along the way, all of them have a suggested instructional procedure. So let's look at one. This is a middle school lesson. This one's on NNIN, and it's called How Dry Am I? It was developed by one of our middle school teachers in our research experience for teachers program. And what it's doing is exploring hydrophobic properties of materials and also biomimicry. Biomimicry is nothing more than how nature already does a lot of great nanotechnology, and scientists and engineers are looking at what nature does and using those properties to create new materials and objects. So what this lesson does, and I just want to walk you through it, is that the students compare and contrast physical properties of superhydrophobic coated materials compared to uncoated materials. So it's a good one for surface tension, and the big idea is forces and interactions. So what they do, the lesson has scanning electron microscope images of a lotus leaf and a magnolia leaf. And we have found that children, particularly middle school, but even older, if you show them a shiny leaf, which the magnolia is, they immediately think that that is going to be the hydrophobic one, but it's not. It's a hydrophilic leaf. On campus here, we actually have a tree. I don't know what kind of tree it is, and it substitutes for our lotus leaf. So usually in the summer, you see us going over to our building and stealing leaves off the poor trees here. So what it does is it uses uncoated and coated samples. The lesson uses fabric, paper. She used linoleum squares, but you can just pick out anything that you want. And it uses Rust-Oleum Never Wet, which is available at like Home Depot, Walmart. And so she coated some sample, she created uncoated and coated ones. And then she had the students explore those samples with water and a variety of other materials. And then she created a demo, and the demo was of pooled water. So essentially she blocked out on, I think she used a piece of tile. She blocked out a section in the middle and then sprayed an edge all around the tile so that water would pool up in the middle but could not run off to where the Never Wet was. So it was a pooling effect. And then she had the students brainstorm about what was going on and why was this happening. So its connection to nanoscale science, even though this is a hydrophobic lesson, is that the lotus effect is the result of nanoscale bumps. Researchers in Germany determined that the lotus leaf stays beautiful and clean because of these nanoscale bumps that have a waxy coating on them, creating a high surface area, high surface tension, so that when the water beads up and rolls off, it carries the dirt away with it. So now we have created things that have, we've engineered surface coatings to do exactly this. So Never Wet is an example, but there's a whole score of hydrophobic materials that have been developed, including pants, umbrellas, plungers. So the next one I would like to talk about is the big idea for tools and instrumentation. And this one's important because nanotechnology would not be where it is without the development of new tools and instruments. So the first one that came out that was very, very important was the scanning tunneling microscope, which led rise to the atomic force microscope. Yes, I am losing this voice. So it's a good way of bringing in the technology and explaining why it's so important. Another important tool is the scanning electron microscope. And I'm old enough to be a dinosaur when scanning electron microscopes were, you were lucky that you got down to, I don't know, 20,000x, and now the ones that we have here at Tech actually can observe single atoms. So it's a pretty amazing technology. So this activity comes from the Nano Center at the University of Illinois, which is the Center, I have cheat sheets here, Center for Nanoscale Chemical, Electrical, Mechanical, Manufacturing Systems. If you go to their website, they have some great lessons. They have 9 lessons and 8 kits that are available. So it's very exciting to go to that website and see high quality lessons. So there's a PowerPoint with this lesson, and it begins with, how do you suggest we determine if the wall has moved? Let me go back. You have usually try to get a good, hefty, strong male student who's going to move the wall. And of course, you can't see a wall being moved, but they think they can do it. So this is the configuration. You show this to the students. I don't usually show this exact configuration. I show them the parts, and I have them brainstorm about a suggested design of how you can see that the wall has moved. So these are the type of things that they have, and this is actually the final setup. We use, this one we use a laser level. The laser level shoots out the beam, and the beam hits a small mirror, and that then reflects back onto the opposite wall. And let me show you a little more clearly. So what we're doing is, excuse me, I'm going to make it quick, I really am. So the goal is that we want to determine if we can move this wall even a tiny amount. And can we develop a tool to see how far it is measured? So if you look at this configuration, that there's a rod which is attached to the wall. If you move the wall, the rod is going to move with it. But if you have this other metal rod, we use rods, it could be a dowel, it's going to move. And that's going to allow us to see how far the wall has moved, because it's rotating, and the arc length of its rotation is equal to half the distance the wall moves back. So going back to this one, as this moves in, this one is rotating. So we do an initial measurement, and we put an X here, usually with some sticky notes, and then they move the wall in, and it tends to move the laser light here. And through a lot of math, which is a great math lesson, they figure out how far the wall has moved. Now we can't see that wall has moved, and the lesson goes on to have them figure out in various conversions how much the wall has moved. And it doesn't move much, but the wall does move, and the students are always amazed that the wall has moved. It's really great to use this one if you have a strong outside wall. Inside wall tend not to be really good because they move a lot, but those good sturdy outside walls are excellent. And how does this relate to nanotechnology? This is how an atomic force microscope works. This is the sample that is being scanned by this cantilever tip. This tip is down to 1 to just a few nanometers. It scans across, and again, we've got this laser coming in that is going to go up and down depending on the force that it is interacting with. And a detector looks at these and creates an image. Think of it very much like sonar scans of the seafloor. Instead, we're doing it down at the nanoscale. So this lesson is a great lesson to let kids do some math, see how we can measure forces that we can't see, and they get a really great introduction to the tools of nanotechnology. The next one I want to look at is the big idea, self-assembly. So this is the one under specific conditions that materials can spontaneously assemble into organized structures. And so this one, we want them to understand what the process of self-assembly is. And we do this through a lesson that came out of the Journal of Chemical Engineering by Brett Criswell, who's now at the University of Kentucky. It's called Connecting Acids and Bases with Encapsulation. What it does is it provides students with experience in encapsulating materials. And they'll become aware of the importance of the scale of these capsules and how they interact with biological systems. So this is not only a great chemistry lesson, it's also a great biology lesson, again, using that interconnection of nanotechnology. And at the end of it, we let them explore how these capsules are being used to either treat or detect cancer. So it all starts out with a simple 6-well microplate. And what happens here is the students are given 2 pipettes. One is sodium alginate with starch, and the other is sodium alginate and iodine. So we're going back, we've taken Brett's lesson and done it with the typical starch iodine lesson that many people use. The top well is going to receive drops from the pipette, and the bottom one is going to receive drops from the second pipette. So you've got starch beads and iodine beads. These then get transferred to the starch solution and the iodine solution. But I want to talk a little bit about the sodium alginate because I think it's very important at this point that the students understand that these are cross-linked polymer spheres and that these spheres are not solid, that there are openings in them just as there are openings in cells. So think of sodium alginate as spaghetti strands or filaments. The sodium alginate strands have a carboxyl group, this CO2 minus. So it's a carbon and 2 oxygen, and it's got a single negative charge. When the sodium alginate solution is combined with the calcium chloride solution, the calcium ions have a Ca2+ that can attach to various strands of the sodium alginate, creating cross-links. And this is how these cross-link into a variety of strands and become gel-like spheres. And the students love looking at these spheres. Now this lesson is probably more for high school students, but on Dragonfly TV, they did a great one using edible spheres and encapsulating chocolate and strawberry syrup. And we've done that with middle school groups, and then they get to eat them and they love it. This is what the spheres look like as they begin, and then depending on what solution they are, you can see better. You can see in this bottom one how the purple starch iodine complex is shown very clearly. So what is encapsulation? We use encapsulation all the time. People don't think of it. Scratch and sniff stickers. Essentially, when you scratch them, you're releasing those micro scents that have been encapsulated. So the pressure erupts them so you can smell those. Aspirins are typically coated, so with microencapsulation of the aspirin so that there's slow release and it doesn't hurt your stomach. Carbonless paper, again, it's a pressure one. When you write your name on the carbonless paper, those things are opening up and creating your carbon copy. And then there's actually pressure activated adhesives that do not work until you put pressure on them. And these are just some examples of nanostructures that can be used. A lot of these are used in research, but I want to talk about a couple of these. So we can use these encapsulated nanoparticles for imaging and detection of diseases. So let's look at a quantum dot. And a quantum dot is nothing more than a nano-sized semiconductor. They have unique optical and electronic properties. Many types of these emit light of specific frequencies once electricity or light is applied to them. And this frequency of light is very important. And they can precisely tune these by changing the dot's size, its shape, and its material. So let's have a quantum dot. It's got a conjugated protein that's there to detect mutated receptors on cancer cells. So here's the population of cells, cancerous and non-cancerous. But we got this little thing here that we want to fit into the mutated cells. So this is a great way of illustrating to kids that something really small can be used to detect a terrible disease. So researchers are using the fluid Mosaic model of the cell membrane to determine how we can get things across the cell membrane, such as quantum dots. And here's an excellent one where they have put something on the outside of this quantum dot that allows it to enter into the cancer cells and therefore targeting treatment. So they can shine light onto these quantum dots, which then would emit light and kill the cells. Here's a great image of quantum dots in this poor mouse. This poor mouse has various, you can see they're tuned for different colors. This allows them to determine where the cancer is, and for a surgeon, it would allow that surgeon to go in and actually cut out the cancerous material and not take the healthy tissue around it. The last lesson I want to go over is mixtures in nanotechnology. Again, this is an NNIN lesson. I hope you realize that what we have done is to look for the lessons that we really like to share with teachers. So if we find a lesson that's with another group, we like it, we share it. So the purpose of this lesson is to help students make the connection between the classification of mixtures is based on the size of the particles. And we've done this lesson several times at NSTA, and we have the teachers come back to the booth, and what they say is, I've taught mixtures all my life, and I never realized I was teaching nanotechnology. So this comes under the big idea, size-dependent properties. So properties of materials can change by size. So this one, the properties of mixtures are very dependent on the size of the particles that are within mixtures and solutions. So where do we use this lesson? As I said, many teachers, most teachers, particularly chemistry and physical science, will be teaching mixtures. So you can use that as an introduction to mixtures or as a review activity of mixtures. The students will get a lot of cards. And these are just examples of the cards. But they get a lot of cards. I think there's about 15 or 20 in the set. And they have to decide on how they want to separate them. They can use any characteristic that they want, but they need to come up with a list of the characteristics on a sheet of paper and then list the cards that belong with each of these characteristics. Once they've done that, we then talk about the classification of mixtures. So we have heterogeneous mixtures. These are the cards that go into that. The colloids, these are the ones that go into that section, and then solutions. But we always have a really good discussion with the students about how they came up with their classification system before we move on to the actual classification system. So what does this have to do with nanoscale science? Well, most people don't realize, but that solutions, colloids, and suspensions are totally based on the size of the particles. So a homogeneous mixture are solutions that have particles that are too small to settle out, and they don't scatter light, and they tend to be 1 nanometer or less. The colloids between 1 nanometer and 100 nanometers have particles that are too small to settle out, but they scatter light. And then the other heterogeneous mixture is the suspensions. And they have particles that will settle out over time and will scatter light. With this lesson, we also create 4 or 5 vials of liquids that show solutions, colloids, and suspensions, and we take a laser light and show them which ones will scatter light and which ones don't. So resources. NNIN is a website still up and running, but it will be going away. So on that website, I said we've got about 100 lessons. We also have on there something called our reference sheets. So we have reference sheets for chemistry, physical science, physics, genetics, and biology. And essentially, it's all the formulas and information that students need in those courses. All of the NNIN materials are migrating over to NNCI Net. It will come out in our phase 2, which is just getting started. On the NNCI site right now, we have a teacher resource brochure that has a link to a variety of lessons. And then we have a long list of external Nano Education resources that goes beyond this teacher resource brochure. Another wonderful site, of course, is nano.gov. You know about that one because you are part of this webinar. And they do have a wonderful searchable database that's on NanoHub. The NNIN website also is a searchable database. NICE Network was another large informal nanoscale network, Nanoscale Informal Science Education Network. They have a lot of materials on there that make great demos for the classroom. NanoHub, as I said, has the NNCO searchable database, but they have a whole bunch of other simulations. They have other lessons. It's a really excellent site. The University of Wisconsin-Madison was probably the front runner of developing educational materials. They were focused on material science, but material science and nanoscience are so closely interrelated that this is a great website. They have not only lessons, but they have videos on how to make materials and how to do the lessons. And also at Wisconsin-Madison is the Institute for Chemical Education, and that has a whole section of lessons on nanotechnology. These are not the only resources, but these are some of the ones that we have used in the past and I think is a good place to go to. And now, questions or suggestions before I lose my voice totally.
Thank you, Nancy. I think you're going strong. We have a couple of questions. Mostly the teachers are really interested in how available these lessons are. I saw that the somebody asked specifically about the wall lab and also about. Oh, go ahead.
Okay, so the wall lab is free for download. Almost everything that we have ever used is free for downloading. The Journal of ChemEd one, you really have to go to JCE. We are allowed to distribute it in workshops. We have permission from the American Chemical Society to do that. And if you don't have access to JCE, you can just email me and I'll send you the whole thing.
Oh, thank you, Nancy. And then as a addition to that, when you said they're all free to download, what about the any expensive equipment or materials that the teachers have to get?
So the philosophy that we have done, so for our lessons, is we always want, and when we do workshops, we want stuff that's cheap, 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 because teachers don't have much in the way of supply money. So a lot of things that we have done our workshops on tend to be cheap supplies that you can get. We do have one lesson on quantum dots that now has gotten to be outrageous, because in the beginning the quantum dots for the classroom were $100 for the set, and now you have to buy a minimum of 3 sets, and it's $1,500. So there's an example of how it's changed. But the majority of our lessons really used very inexpensive materials. For the move the wall lesson, we use a surveyor's laser level, but you don't have to. You can jerry rig it, or you can ask parents if there's anybody who does stuff that uses that type of a laser level. And a lot of time parents are willing to let you borrow it, but you don't have to use that.
That's really great to hear. Thank you. And
oh,
did you want to say anything?
Never Wet at Ollie's for just under $6. I'll be looking for that one.
They're going to have a run.
I will give you some hints on the Never Wet. It's a really nasty process. It stinks. It's best to do it in a hood or outside. But they've just come out with one that's a fabric one, and I love it. It works really, really well on fabric. And it doesn't smell as bad, and it's not a 2-step process.
Great. I have another question for you about, you've mentioned a couple of times professional development and having that lab something you can pass out. Do you have any information? Is the NNCI offering any professional development workshops for teachers this summer, perhaps?
No.
No.
We were supposed to do it at Georgia Tech, and I just got told that my proposal had been turned down, so we will not be doing one. I do know that Montana State is supposed to be involved in doing teacher workshops. I don't know if they're going to be doing them this summer. It's part of their, I think, part of their master's program. The University of Nebraska at Lincoln also has indicated that they're going to be doing workshops, but I don't know if or when they're going to be doing it. And that's part of year 2, is how do we organize and get more workshops going. We will be doing one. We will be doing one at NSTA next month.
Oh, nice. Yes, that's an excellent plug. Thank you, Nancy. Yeah, next month at Los Angeles at the National NSTA, there will be a workshop on nanotechnology from NNCI. And I also think that UC San Diego, which is also an NNCI node, will have an RET this summer, from what I understand.
Yes, a couple of the sites have RETs, I think.
Research experience for teachers.
So I think Northwestern is also going to do one. If you go to the NNCI site, you can click on the various sites, and if you go to the education section, it should tell you which ones are offering RET. And I know that several NNCI sites are getting ready to write an RET proposal to get an NNCI RET program like we had under NNIN.
Great. And then I just have one more question for you, and you've already sort of addressed this, but when you were talking about how important it is to first start out with the size and scale in the classroom, you mentioned having the micro nano signs up for teachers to help kind of implement that. Do you have any other examples for how to implement the size and scale in the classroom, or that you'd like to share?
Off the top of my head, I think, doing the size and scale activities is always excellent. Using these interactives, there's some of these interactives are just absolutely amazing. Um, and then, as I said, the classrooms, there's another really good lesson out there that was developed out of the University of, I think it's either Louisville or Kentucky. Um, it's called the Dime Walk. And if people are interested, I can't think of, it was in, I think it was in one of the NSTA journals, and that has the students walk through the building going down in size. But they start out with a giant dime and a person sitting on it, and then they have to figure out how they're scaling down as they walk down the size scale.
Oh, that sounds like fun. I'm just going to slide us back to the size and scale interactives that you mentioned, just to show that they're all here. And as I said, this will be archived, so you'll be able to look at these once this is all up. So unless anybody else has other questions they'd like to post, I think we're actually going to finish a little bit early, which is always better than finishing a little bit late, and we'll let Nancy rest her throat, and I hope you start to feel better. Thank you very much, Nancy, for doing all of this.
Welcome.
And as I just said, this was all recorded, and it'll be posted on the NanoTube, our YouTube channel, and you'll also be able to find it under nano.gov/public webinars. And as Nancy also mentioned, a lot of the resources she discussed you can find on the NNIN/NNCI eventually site, and also NanoHub. With that, I want to thank you all for joining us this evening, and I will let you know when we have our next webinar. Thank you very much.
Thank
Good night.
you.